Welcome back to the series where we are diving deep on all of the things that you avoided in science class in high school. This is Chemistry of Indoor Environments, which was a 10-year-long program. Today, we're talking with Joost De Gouw, who is a researcher who did some interesting stuff around fires. So we're going to talk specifically today about the wildfire that happened in Boulder in 2021. This was part of our series Home Diagnosis season 3. It was episode 1. So if you get a chance to go watch that episode, I'm linking it on the screen right now. It's amazing. This presentation is not part of that. This is new stuff. And in fact, let me just say before we begin that this is a perfect example of why people are afraid of chemistry, because his presentation is going to start nice and easy, and then it takes a turn. And so my brain was hurting. I had a long conversation with Joost. He answered a bunch of my questions. I will try to make everything as clear as possible to you. Please do make sure that you're stay tuned to the end, because it will get a little painful. Here we go.
So our indoor air research took a turn on December 30, 2021, when this urban fire occurred in Boulder County. So what you see here in this little movie is Boulder in the foreground. See here, these are the dorms for CU Boulder. There was a grass fire that started here, fueled in very high winds. And then it burned into Louisville and Superior, which are here up on the hill, and burned over 1,000 homes. So this happened in the middle of winter, December 30, 2021. So what caused this fire in 2021? We had a very wet spring. This graph on the left here shows you the precipitation in 2021 compared to the 19 previous years. So you see this wet spring, blue sticks in the spring months, and then we had a very dry fall. So what happened was grasses grew very abundantly in the spring, and then they dried out in the fall. And then when we had very high winds on December 30, a grass fire, which were common, grew out of control and caused this fire. So to illustrate the high winds, I brought this photo from Steve Brown showing a Sprinter van that blew over.
By the way, I think that this is a great example of like things that seem really good and helpful and hopeful for the world, then turning into like the recipe for disaster. So just a reminder, the pendulum swings both ways, good things and bad things. They are constantly linked with each other. And that's just that, as a father of 3 young children, that helps me feel better about like the continuity of life.
So as a result of this fire, more than 1,000 buildings burned, 149 damaged, and only 2 lives were lost. Tragically, 2 lives were lost. But considering what happened, that was a very surprisingly low number. So the map on the left shows you the perimeter of the burned area. So for those of you who have been to Boulder, Boulder is up here. This is US 36 that you come in on. And the fire was on both sides of the highway, but it had to stop somewhere. Eventually, the winds died down and the fire stopped spreading. Also, some homes were much more resistant to fire. And so the situation that you have then is that a city block that completely burned down was surrounded by homes that did not burn down. So that was good news to the residents, of course. Their homes didn't burn, but they were exposed to very heavy smoke on the day of the fire.
Incidentally, if you want more advice on how to make your home fireproof, we have all that stuff in that episode of the Home Diagnosis Season 3 that I was pointing out. It's called Where There's Smoke, There's Fire.
And that smoke led to significant impacts in many of those homes. So here are some pictures from inside one of the homes, the unburned homes on the previous slide. And you can see ash and soot everywhere in the home. This is right behind the front door, but this is on top of windows, windowsills, stair railings, etc. It's everywhere in the home. And also, importantly, these homes smelled very bad. People complained about strong burn smell indoors, and that made this into an indoor air problem.
Okay, now for it to get on top of the windowsills and on top of the window frames, it means that these particles were in the air. We're going to come back to particles more in this talk, but this is something that, like, this stand 6 feet away from people during COVID times is totally insane. That is not how this stuff works. It's floating in the air. It can float for hours or days or weeks in some cases. This stuff was floating in the air, and then it came to rest on all kinds of horizontal surfaces, no matter how high they were. So the cleaning that needs to take place now is what they are starting to research.
As a result of these impacts, many people did not return for weeks, if not months, and some people that we worked with never even returned to these homes. So we decided to make some measurements. There is very little literature. There's now a little bit more thanks to the CASA Chem campaign, but there was very little literature at the time to talk about smoke impacts inside homes. And so we teamed up with some collaborators from engineering, Nina Vance, Mike Hannigan, Colleen Reed, and we instrumented one home very heavily. You can see it here. We had a Focus PTR TOF. We got a small TOF Werk instrument, a Focus ELF. We had particle sizing instruments from Nina Vance's group. And also we wanted to make more measurements in other homes. And so Mike Hannigan had these low-cost sensor packages that were all in this home to be compared against each other. But after that, went to 12 different homes for more measurements. So we did this for about 5 weeks. After those 5 weeks, the home was cleaned professionally, and we also have some data from what happened during that time.
Now, first, let's just go into the instrumentation a little bit, because this stuff is really interesting, I think. The TOF that he's talking about, these TOF work and PTR TOF, that stands for time of flight. This is a kind of a mass spectrometer, which is a machine that separates molecules. So there are molecules floating around in the air. Getting them into the air is one of the jobs of these researchers. Is like, we've got all these chemicals that are hanging out on surfaces. We need to get them up into the air. So they do all kinds of things, tricks to make that happen. In this case, there's plenty that's just in the air naturally because it's off-gassing from the house. So they didn't have to do much. But the time of flight spectrometer, the way it works is you take this kind of like it's an electric field essentially, and they're ionizing molecules, and they give each of the molecules the exact same charge. And what that means is basically you've got a machine that has this long tunnel. You could think of it as like a racetrack, and it's got like a certain shape, and they know exactly how long that is. And so when they give the molecules this kick, basically, of that ionization, of giving an electric charge, then it races down the track, and the time it takes to do that, time of flight, gives them basically the inertia, or the the characteristic that would lead them to understand what the weight is. And unfortunately, because molecules are very complex, and if you've seen maps of them, there's like lots of different things going on. Some of them might have very similar mass. And so then you use the gas chromatograph, which is this over here, this GC. That's a little bit more of a fine-tuned thing. So that is a long track, but instead of kicking the molecules through and seeing how long they take to go down the track, what that is it's coated on the inside of the pipe with something that is then able to separate it. It kind of affects different molecules differently. So then you're able to separate out things that would have the same mass, and then it can tell you, oh, that one was reacting with the coating that we had, and so this one must be done. And then it'll give you a list of what the ingredients of your air are, basically. The particle sizing that you see right here from Nina Vance, and you can see Nina Vance all over our channel. I'm linking stuff from her on screen right now because she's awesome. These particle sizers are giving you a list of the amounts of particles per size range. And one thing that I want to show you is this. This is an X-Tech 6-channel particle counter. And this thing basically is doing the same kind of job as that. And I actually showed this to Joost, and he said, yeah, that's actually a pretty good. So this is like, in my opinion, the best thing that consumers and prosumers have access to. Like me being a prosumer, we're not academic researchers. Like this is the next step is that machine that she's got. Bottom line is what they're measuring in this picture is all the things that you can smell, which are mostly chemicals, and all the things you can see in the haze in the air from smoke, and that's mostly particles. And also, by the way, these ropes that are hanging down right now, I was like, Yost, what are the ropes for? What is that? And he was like, oh, that was a decoration because this was actually a house. It looks like we turned it into a lab, but there's like decorations and paintings and stuff like that around the house. The last thing is that the professional cleaning that they did on February 7th and 8th, I'm just going to let the cat out of the bag. It didn't work. I was like, did it work? He said, and he kind of said, well, da, 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 da. And what they were able to do is actually keep monitoring the house after that happened, because the people who lived here also owned the house next door. They were able to move their equipment over there while the company that came in, which is basically a disaster relief company. And this is something, sadly, that all kinds of disasters across the country, hurricanes, fires, floods, are going to involve this process of air cleaning. It's like basically they're bringing in chemistry generating equipment, bringing in UV, heavy UV. They've got ozone. They've got, they're creating hydroxyl radicals. They might be creating hydrogen peroxide also. And you'll see a graph in a few minutes of another air cleaning device that actually did work. This one worked about as well as that, which is not very well. It's a Band-Aid. And what they found is that it made the home infinitely more polluted. Not infinitely. He would hate it that I said that, but like a lot more polluted for a period of time while they had these machines running. And then guess what happened as soon as they turned the machines off and they went home? The levels dropped right back down to where they were. So he said this kind of cleaning does not work. And we know. The reason you won't hear that a lot in the media is because as soon as somebody says that kind of thing, a big company will come and say, we're going to sue you for $300 million for defamation unless you blah, blah, blah. It'll probably happen to me at some point. I'm not going to hold my breath. We're just going to keep on fighting the good fight. But like, just know that that kind of stuff is happening out there right now. So if you have the choice, just do what he's going to suggest in a minute, which is just wait.
So many VOCs were enhanced indoors and gradually decreased over the course of our study. So it took about 4 or 5 weeks for the VOCs to have cleared out of this home. That was longer than we expected at the time. We were thinking of the effects of painted surfaces, for instance. We would have expected that it was hours to days for some of these compounds. It took days to weeks in this case.
So there's these spikes over here. All these, by the way, are what are called aromatics. So you can smell basically all of these. And I was looking at this list, toluene and benzene. Those sound like things that would be associated with like gasoline. But actually, it turns out that when you burn wood, like in a forest fire. And in this case, this was a grassland fire, which is a little bit different. But one of the ingredients in woody materials is lignin. There's cellulose and there's lignin. We talked a lot about this in the episode 9 of Home Diagnosis Season 3, which is all about mold. And lignin contains a lot of these compounds. It's built in. And so then when you burn it, they get released into the air, and that's where they can start to do damage. Again, things in the air are bad because then we breathe them and our kids breathe them. And where they are built into things, that's fine. These spikes right here, where it went down, and then suddenly at around day 16, 17, it spikes back up on these 3 graphs here. These are probably, Joost was saying, based on weather outside. Like the weather changed pretty drastically over the next couple of weeks, which is like the first 2 weeks of January is what we're talking about here. And he said that there were warm days, cold days, and also the wind would blow and then not blow. And since it spiked outside and then it spiked indoors, but the spike indoors wasn't quite as abrupt as the spike outdoors, he was like, yeah, it's probably based on outdoor chemicals getting brought inside still, because the outside was still all burned up too. So at the end of these 5 weeks, at day 35, all of these levels are basically steady state, safe levels. That's what your house is right now without any wildfire going on at all. So he said after about 5 weeks, the levels had basically, what we had done is if the house is just sitting in the middle of the smoke, it becomes a sponge. and it soaks up all of these chemicals that are floating around the air. And then when the smoke goes away, then the house is the sponge, and it starts wringing out and drifting the chemicals back out into the air. And then after 5 weeks, it had completely kind of depleted itself down to what we're considering normal levels.
So we looked at the composition of the VOCs, obviously. Things we could compare to are the composition of indoor air, as it's been reported in many different studies. We used the Logue paper from 2011. And then we also compared to the composition of burning lumber. We took lumber because that was what we had available. And then we tried to explain the observed composition of VOCs in terms of these two sources. And the graph shows here how that works for one sample. So you can explain the VOC composition as a function of these two sources.
Just to paraphrase, they've got a mountain of chemicals that they're monitoring inside. No way to separate out what is supposed to be there and what's not supposed to be there. And they took these, research studies that had been done before and said, okay, well, this is kind of what we assume homes are going to off gas. This is what we assume outdoor wildfire is supposed to off gas. So since nobody's really done this before, we're going to try and be like, okay, well, this is supposed to be here and this is supposed to be here. And that might explain the shape that we're seeing or the amount of VOCs.
So we did this for all the days of the experiment, and we get pretty consistent results. The fit parameters are here at the bottom, and the R-squared value for the quality of fit is pretty consistent from day to day. And what you get then from this fit is a source attribution for all VOCs. This is the result for benzene. So it shows you this decline in concentration, and then the contribution from indoor air, and the contribution from the fire impacts. So the contribution from the fire impact is larger than the indoor air component. And we also see that the fit describes the benzene observations quite well.
Okay, so this fit parameter is the bias that you need to build in to say, okay, here's model what we need to add to the measurements or to add to our assumptions so that then the model, the computer model, matches real life tested conditions. And so what you're seeing here is this is the amount of indoor contaminant contribution that should be coming from the indoor building materials. Here's the amount that we know happened from the burned lumber. And then basically it ends up being like doing what it's supposed to do. And so once they fitted this parameter, this like extra coefficient into the picture, they were able to account for this dotted line right here says 60% of the variability of their measurements were accounted for by this fit. 60% does not sound that great. So Joost told me that they actually have recalibrated and taken some more measurements, and they've been able to really get that thing up to 90%. But there is still this mysterious 40% in the original study and 10% still that's like they don't know what is going on. So this is, again, why this science is happening right now and why it's so important. One other thing that I wanted to say is that the VOCs, the way that the mechanism of this works, if you haven't watched a lot of these CIE videos, is that the VOCs come inside, and volatile organic compounds means that they like to be in the air. They would prefer to be in the air than being on surfaces, but they're perfectly happy to be on surfaces. In fact, they find that they do that all the time. So they come into the house, they sit down on surfaces, and they're kind of like, it's not bonded, but like you consider that they're sitting there and they're not going anywhere. Then slowly over time, just like what we were talking about with the HRV kind of battery analogy in Michael Link's presentation, it will give off a consistent amount of that pollution over those 5 weeks until finally we reach the like, oh, we've depleted it enough so that now it's safe.
Now, this was an urban fire. It's not a wildfire. So all of our emission factors for vegetation are not entirely appropriate. are there VOCs that are coming from non-biomass fuels? So that's a question we keep working on. We're hampered by the fact that there aren't a lot of emission factors from building materials. But halogens are a good place to start when you're interested in this. And so we looked at, we were thinking about brominated flame retardants. And there is some literature on the compounds you get from pyrolysis of brominated flame retardants. And so we had some target compounds to look at. We did see some ions here on the right that were high when we were sampling indoors, low when we're sampling outdoors, that have bromine in them and that have molecular structures that are very similar to the pyrolysis products. So we need to do a lot more work on this.
Okay, so the graph here shows indoor measurements, outdoor measurements. They were just kind of like switching off indoor, outdoor. You can see that the outdoor levels are really low. This is part of this thing about like, hey, indoors is way more polluted. You measure almost anything and it's going to show up like this because the indoors hangs on to stuff. You get this longer residence time. So the brominated flame retardants come from furniture and foam insulation. All foam insulation and almost all furniture, unless it's California recent, I can't remember what exactly the standard is, but they have now a way for furniture manufacturers to not build in flame retardants into the foam in the furniture. And that's a California certification. You also have chlorinated flame retardants that are from like electronics, for example, like this thing that I just showed you has flame retardants built into it. And so if I burned it, or you burned a vehicle, which tons of them did during this fire, then we have this extra signature, which like might be part of that 40%/10% of the variability that's not accounted for by their model. But that's kind of what he's saying here is that we don't have those what did he call it? The emission factors have not been studied enough, and it's because this science is developing right now.
A lot of people were asking us what can we do to improve our indoor air. So we did experiments with Corsi-Rosenthal boxes with carbon filters. And we found that they actually worked very well. I know there are some conflicting results about this in this group. We found that they worked really well. These are our results for some aromatics. You know, they're high before the box comes on. We turn it on, and they really go down to levels that are more close to ambient, to outside. But then, as a lot of people have reported, when we turn off the filter, the levels bounce back up to where they were. So it's not a permanent relief.
We have called this on our channel before a comparetto or a filter box. Basically, like nothing is original. Everybody's invented everything already. So this is named after Rich Corsi and another researcher named Rosenthal. You can see Rich Corsi on our channel. He's awesome. These things are super cheap to build. So if you can't afford to buy a portable HEPA filtration unit, build one of these. It's a $20 box fan and then some filters that are like at most $25 a piece. So less than 150, 200 bucks tops. You're going to get a pretty good machine. Now, his thing of like, it's not a silver bullet. It's not going to save you. It has to be running. And they tend to be a little loud. So it's a little annoying. But you can see how good of a job it does right here. When you activate the fan, it really pulls it down. So I'm going to recommend this to a lot of my clients that are like having to work through odor issues, because like while it's an emergency, you just need something to give you relief, and this can really help.
We found that they remained effective during our study. We didn't use these all the time. We wanted to observe the house as it was, you know, without the effects of air cleaning. So what this graph shows is the percent removed for benzene, toluene, and C8 aromatics as a function of the runtime of a fan. So the longer you run them, the more you remove eventually. But we also saw that this removal fraction didn't change over the course of the study. I should add, though, that the total runtime was only on the order of several days. So,
okay, now what I take this to mean, and I asked Joost this, and he said, yeah, I basically agree, is that right around 4 hours, we have reached the point where we kind of have steady state, like it's steady state-ish. where we've removed 60% of the stuff in the air. And by stuff, I mean these three little things here, benzene, toluene, aromatics. And it's not going to remove a ton more after that. So it's kind of a point of diminishing returns around the 3 or 4 hour mark. What that means is that if you have a situation where you've got this disaster that's happened and you want to avoid this, and by the way, if you watched the school session from last week, you saw that people's opinions about what the air quality is like does not match with the actual data of what the air quality is like. So we're not great measurement tools. So if it doesn't smell that bad, it doesn't mean that nothing is wrong. You should still plug in one of these things and then leave it running in there for 4 hours before you go in and start doing stuff to try and clean. So once you've got it up to 4 hours, you've removed about 60% of the stuff, it's still pulling out. And what is happening here really is that we've reached this steady state of the filter box removing while the home emits. So it's basically a 1-for-1. It's not a 1-for-1 because it's only 60 to 70%. But for every bit of pollution the house is putting out, then these filter boxes are grabbing most of that. And so then it's like a relationship that's just, you keep it running and it keeps on doing. It's not going to get any better than that. And remember, as soon as you turn that thing off, it goes right back to the terrible situation that you were in. So don't turn them off.
And then, of course, we have the full mass spectral information for what gets removed. And this is what that mass spectrum looks like. So it's the percentage reduction of signal as a function of M to Z. And you see that the removal fraction is best case somewhere near 80%. There is smaller removal for very light VOCs, and other groups have reported that yesterday on a poster. There's also a small drop off towards high M over Z that other groups have seen. What we also see is, of course, some variability here that may have to do with the functionality of the molecules, and we need to look into that more.
Okay, now this was very confusing to me. Mass to charge ratio is going back to that time of flight mass spectrometer. That's how they initially measure the weight of these molecules, is they give the charge and then they watch it race through the thing and they know its mass then. So the mass to charge ratio is basically another way of saying these are the weight of these molecules. And what you can see is that a lot of them got pulled out to the tune of around 60%. He's saying like between 40 and 60%. I'd say it looks pretty solid around 60 to me. But again, I'm not a scientist. I'm not looking at this the right way, probably. All of the molecules that are floating around in the air are represented on this. This is the yearbook of all of the molecules that are there that day. So none of them are missing. There's not molecules in here that just didn't go through here. This right here shows a molecule that didn't get caught by the filter at all, basically. It just goes right through it, just like it's not even there. So there are molecules like this one right here, this one right here, that don't care that you put a carbon filter in the way, and they're just going to stay in the space as long as they feel like. That being said, most of them are going to do what you want, which is get caught on the filter, again, to the tune of 40 to 60%.
But overall, these cleaners work very well. So with that, I'd like to conclude. So smoke VOCs were retained indoors for weeks. There was some evidence for emissions from the burning of man-made materials. We found that the CR boxes with activated carbon were very effective at removing VOCs. But as a lot of people have reported, there is good evidence for the presence of very large VOC reservoirs indoors. We don't really know well what they are, so more work's required there.
Okay, now these VOC reservoirs, I want to give a hint because Joost said that there was another presentation in this series, which you're going to see, given by Elliot Gall, and he did some work on drywall. And he said that that might turn out to be one of the major reservoirs where these VOCs are getting sucked in and then put into a sponge to stay around. So again, you're going to see that. Stay tuned. Make sure that you're subscribed to the channel so that you get that.
So this work was supported by Sloan. We also got some support from Ceres. We had to get started with these measurements on a timescale of days. So thanks for their help and also for NSF Rapid. Thank you.